Hello, Block 5. I'm really sorry that I am not able to be at school today to play with you. My daughter's feeling a little under the weather. So anyway, I just wanted to walk you through a couple of last things from the derivation that we started when we were together last time. We didn't quite get through for you to be able to do the analysis with the resonance tubes from that lab. So I wanted to make sure that you knew how to do that. So here we go. I'm just going to revisit what we did last time. We were talking about the standing waves on the string, and we have this one up here, the simplest standing wave, and from that we used our equation of velocity, which equals lambda times f. Solving that for f, we got ourselves an expression for the frequency of the standing wave that would, the simplest standing wave that will stand in that string based on the velocity of the wave in the string and the length of the string itself. And then we went through and we looked at some more complicated standing waves, also again in a string that's fixed at both ends. So hopefully that made some okay sense. So we had F1, F2, and F3, and it looks like that may have been where we ran out of time, but it may appear to you, or I hope it appears to you, that there is a nice pattern that's going on here where we've got F1 that equals V over 2L, F2 equals twice V over 2L, F3 equals 3 times V over 2L, and we can actually then just kind of propagate that out to get ourselves a very general expression for the frequency of any harmonic. Harmonic means, in this case, the number of antinodes, but it's the number of the standing wave that we've got. F sub n is equal to whatever that harmonic value n is times V over 2L. Okay, so again, n is the harmonic, and this is the frequency of that harmonic, so how fast the little click, 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 clicker was going on the standing wave lab that you did. V is the velocity of the wave, and that's dependent both on how tight that string was, which is why I told you not to change the tension throughout the lab. It also has to do with the mass of the string. If you have ever seen or played a stringed instrument, you know that different strings on that instrument have different thicknesses. It's so that they can have sound waves moving at different speeds. So that's where that comes from. And then L is, of course, the length of the string. Okay, so that equation that I'm going to put a big box around because it really is important, that equation is the one that you're going to use when you're doing your lab analysis for the standing waves lab, the one that we did most recently. Depending on the question you asked, you may, excuse me, need to be a little bit clever about how you rearrange that so that you can get a straight line, but that is the equation that you will use. So that is how we derive standing waves in a string. But not all musical instruments, if we're going to talk about musical instruments, for example, use strings. Many of them have air columns. So any of the band instruments that you can think of are all air columns. And fundamentally, there are two different kinds of air columns. There are flutes and then everything else. So by flutes, I mean flutes and piccolos, those things that you blow over. So there's actually two open ends. If we look at an open-ended air column and we think about how air travels through that air column, because it's open at both ends, the air is free to move back and forth and back and forth. And so in terms of a standing wave, that would be an antinode. Now, I'm going to reiterate, because we've talked about this before, that a sound wave or an air wave traveling through a musical instrument, like a woodwind instrument or a brass instrument, is going to be a longitudinal wave, not transverse. But because it's hard to draw longitudinal, when I draw this, I'm going to draw it as a transverse wave. So I'm really talking about the pressures here. So that all said, if I'm going to have a simple standing wave, again, in a flute or a piccolo or, you know, any of those types of instruments, again, where you're blowing across the opening, you're going to have antinodes at both ends and a node in the middle. So your standing wave is going to look something like that. And if we look carefully at that, we go from a crest here to a trough there, and very similar to the string, the length of the tube is going to be equal to 1/2 lambda, or we can say that lambda is equal to 2L, And when we use our equation from above, F is equal to V over lambda, well, that means that F1 is equal to V over 2L. That probably looks kind of familiar if we refer back up here. Oh wait, it's V over 2L. Same thing. We could go through, and if you would like to, you are very welcome to go through and do the derivation, but I am going to ask for now, just kind of for the sake of time, that we believe, and again, I don't want you to just like trust it, but I want you to go through it yourself if you would like, to show that that will be the same thing again for this standing wave in a string, standing wave in a flute, or open air column. The frequency will be equal to n times V over 2L. So that's all well and good. You say, why are we going through this process? Well, it's kind of nice to know that flutes and stringed instruments all hold standing waves with the same relation. All of those other musical instruments, so you've got your clarinets, you've got your trombones, you've got your saxophones, any other brass instrument, woodwind instrument, they hold standing waves in the same way that an air column holds a standing wave. An air column, I don't know, that you might like strike a tuning fork and then find a resonant height at, like the lab that we did. So if we look at that situation, I'm going to draw this one vertically just so that it looks a little bit familiar to you based on the lab that we did. So there is a column of air. Here's your water down here. And really, when you were doing the lab, everybody was very concerned about what height the water was at. But really what we care about is what the length of the air column is, okay? As we were talking with the flute, an open end is going to be an antinode. So here, if we just want to kind of imagine this, this is like where your tuning fork was hanging out. Does that make sense? The air right up at the very top is free to move. It's able to vibrate. It's able to move up and down, up and down. But at the water, it's not free to move. There's going to be an antinode there. Or excuse me, there's going to be a node there. It's not able to move. So the simplest standing wave is going to look something like this. Okay? If we look carefully at that, we can try and figure out how much of a wavelength that wave is. So we're going from a crest or a trough to an equilibrium point. So instead of going through a half wavelength like we did before, this is really only a quarter of a wavelength. Okay, so this one is fundamentally different. In this case, F, which again equals V over lambda, same relationship that we had before, F now equals V over 4L. So if we solve this for lambda, that's 4L. Okay, so right here we've got something that is very different. It's got a 4 instead of a 2 on that in the denominator. If we look at something a little more interesting or a little more complicated, if you remember when you were doing your lab, some of you found resonant heights both high and low for some of your tuning forks, and that's lovely. So we're going to make this longer length where we also found a resonant length. So here's my new length. In this case, we're going to have another standing wave, which means that we've got, well, we still have an antinode at the top, we still have a node at the bottom, but now we're going to have a node in the middle and an antinode in the middle. So it's going to look something like this. So we're going to go antinode through to a node. There's an antinode and then to a node. And then we'll go the other way just so we can complete the standing wave. Something like this. In this case, now we've got, there's a quarter plus a half, and a quarter plus a half is of course going to give us 3/4, so this is 3/4 of lambda. So F here is equal to V over, well, it's going to be, excuse me, let me erase that, 4/3 L. We don't want to freak out that there's a fraction in the denominator, so I'm going to go ahead and move that thing up to the top. So I'm going to get F is equal to 3 times V over 4L. And that's nice. I mean, it looks kind of similar. It's got the V over 4L part, but you'll notice that the second simplest standing wave in this case has a 3 here. Okay? So the rule for this type of standing wave where you have one open space and one open end and one closed end, F sub n is equal to n times v over 4L. And again, we could go through a number of these and keep propagating it out, and you would find this result. The key here is that n must be odd. Okay, so there are no even harmonics when you have one open end and one closed end. So this is what you're going to use for the resonance lab. So with your partner, I would encourage you to sit down and figure out what you're going to graph so that you can get yourself a straight line, right? It's always about linearization. And I would like you to also think about, well, first of all, using all of your data. So thinking about how you're going to deal with that n. There are a number of different ways to do that. And then also, as I mentioned before, I want you to comment in your conclusion as to what the slope means. And there's a very specific thing the slope means in this case. I want you to think about it. I don't want to tell you right off the bat, but think about what you think that means and see if your result makes sense. Okay? I hope this helps, and if you have questions, of course, let me know. See you soon. Bye.